Good morning, everyone. Thank you for joining us on this webinar on the OCS IO Modules Preview. The presentation is roughly 20 minutes, and if you have any questions, you can ask at any point and we'll get to them at the end.
Hello and welcome to today's webinar. Today we will preview some of the new OCS IO modules that are coming soon. Let's look at our agenda for today. We will start with a quick review of OCS IO. We will then preview some of the new OCS IO digital IO modules that will be available soon. Then we will discuss the requirements for Seascape and firmware so that we can take advantage of these new modules. Then we will also look at the assembly of OCS IO and revisit OCS IO configuration in Seascape. There will be demonstrations throughout, and we will finish with a Q&A session. We will begin by reviewing OCS IO. OCS IO is a family of remote and expansion IO, which is compatible with nearly any Horner controller. Remote I/O is usually located within a few hundred meters of the main controller. Expansion I/O is usually built into the same control panel as the controller. OCS I/O is a ground-up design, which uses an off-the-shelf mechanical package made with purely Horner electronics. This includes an I/O system that is fully integrated into Seascape and the OCS. OCS I/O can fit into your application in many ways, regardless of the Horner OCS controller you are using. Its mix of I/O built into the base can often complete a smaller system, and the high capacity and density of OCS I/O, including the new I/O modules available soon, are also an advantage for larger applications. For this reason, OCS I/O is quickly becoming our primary I/O offering. As with many other expansion I/O platforms from different automation manufacturers, OCS I/O starts with an I/O base. This is the building block we start with before we can add additional I/O. If we look at the CNX IO 116 base, we can see that we have LED status indicators to tell the status of the network connection to the base. From a connectivity standpoint, we use RJ45 style modular patch cables. These are CAN-based, not Ethernet-based. On the backplane, there is a connector that allows you to join up to 8 additional modules, including the base. This connector is designed so that if you need to replace a module in the middle of the stack, you can easily take the module out of the middle and replace it, instead of needing to disassemble the whole stack. One of the unique capabilities of the CNX 116 base is that it offers innovative built-in I/O. This base has 6 I/O points. These include 2 flexible digital or analog inputs, 2 high-capacity DC outputs, a high-resolution universal analog in, and a flexible analog out. OCS I/O offers plenty of additional support for both smaller and larger I/O systems. With OCS I/O, you can have a total of 8 modules per base and up to 16 bases per system, so you can have a very large system for your application if needed. Here we have a list of the original modules that are available for Horner I/O. These include an 8DC input, 8DC output module, a 4DC input, 4 relay output module, some high current relay outputs, as well as AC inputs. We also have a 4-channel analog input card that is high resolution, where every channel is configurable between voltage current thermocouple and RTD. We then have a flexible analog output card, which supports -10 volts to +10 volts. Now let's look at some of the modules available soon, both of which are higher density digital modules. These are a 16-point DC input module and a 16-point DC output module. These modules allow you to have as many as 128 inputs or outputs in a single rack. It should be noted that because our current I/O base already has some built-in I/O, you can only add 7 of these modules today to an existing system. These new modules also have extended temperature specs, which support from -40 to 60 degrees Celsius. These modules also support an even wider range of storage temperatures, from -40 to 85 degrees Celsius. Let's look at these modules in further detail. First, we will look at the 16-point DC input module. All 16 inputs can be configured either as negative logic, which would be considered sourcing for input modules, or positive logic, which would be considered sinking for input modules. This particular module supports both positive and negative logic. However, each input must have the same configuration. All inputs share the same common, and in addition to the 16 input terminals, this module also has 8 0-volt or common terminals. There is also a status LED for each input, as well as a power LED and an OK LED. Here we can see the wiring for this module. As mentioned before, this module consists of 16 input terminals, as well as 8 0-volt terminals that are there for your convenience. Next, let's look at the 16-point DC output module, where each of the outputs can drive loads as large as half an amp. These modules are positive logic only, or sourcing outputs only, which means you are providing the plus lead to your load. This module is divided into two circuits of 8 outputs each, so you have a voltage pin for supplying voltage to the first 8 outputs, called V1, and another voltage pin for supplying voltage to the other 8 outputs, called V2. Each of these 16 outputs are short circuit protected, so if you have a short circuit condition, you should be able to resume your application once you have fixed your short circuit. This module also has some extra terminals for convenience, as well as an extra voltage input terminal and 4 extra common terminals, and the same LEDs as the previous module. Now we will look at the wiring of this module. This 16-point output card is configured as positive logic with 2 groups. This module has 2 V1 terminals where you land the voltage to drive your first 8 outputs, as well as 2 V2 terminals for landing your voltage for driving your second set of outputs. It can be noted that it is not necessary to use all 4 terminals if you're not going to exceed 4 amps as a total on any group. Both of these modules feature removable terminal blocks, which we will soon demonstrate. These are spring clamp based, meaning they are fast to wire. All of the positions on the module are also labeled. From a wiring standpoint, the sizes of these support wires range from 16 to 24 gauge. As well as this, there are no tools required to insert ferrule wires into the terminals. However, a tool is required to remove the wire. To connect OCS IO to your controller, we first need to look at the controller's CAN port. Many of our OCS products, including the XL series and the Prime series, have an open style connector for CAN, seen in the bottom left. This plug is where you land your wiring, and where you place your termination resistors for one end of the network, if the OCS is on the end for terminating the CAN network. For this style of connector, you can use a cable with a modular connector on one side for the OCS IO and an open connector on the other. If you have an OCS with an RJ45 port for CAN, then you can simply use an RJ45 patch cable like you might use for Ethernet. If the OCS IO is at the other end of the network, then it needs to be terminated. This can be done by using an RJ45 termination plug. There are some requirements in order to use the 16-point DC input and 16-point DC output modules. To use these modules, you will need Cscape version 9.9 Service Pack 10 or later, and a CNX 116 IO base revision BF or later. You also need to make sure that your OCS firmware is updated. We have a list of the different firmware versions that are required at a minimum here on the screen. Next, we will look at how to physically assemble the OCS IO. Here we can see the OCS IO, which comes fully assembled in the box. We can also see that the backplane connector is pre-installed. We will first need to uninstall the backplane connector before we can build up our base full of I/O on our DIN rail. We can do this by simply pulling it off the OCS I/O. Once we have done this, we will need to pre-assemble our backplane. In the system in our demonstration, we have 3 modules in our base, which we are able to put together by snapping them together. To make sure that we have the proper orientation for these modules, we have the plug facing the left. Once we have pre-assembled our backplane connectors, add them onto the DIN rail by snapping them into place, making sure they are attached properly. Once these are in place, we can attach our bases to our modules, with our DIN rail acting as a fulcrum. This is what our assembled OCS now looks like. We can note that these bases will usually have end stops on both sides. As mentioned earlier, this I/O system features removable terminals. We will now demonstrate these. Here we have a loose module. When we want to eject the terminal, we will take a medium-sized screwdriver and place it through the orange tab shown until it reaches this silver feature. Now let's demonstrate this on one of the installed modules. Placing the screwdriver through the orange tab as shown before, we then pull the screwdriver straight down, which makes all of the terminal blocks pop up at once. Another feature of OCS I/O is if you use ferrules, such as the one shown, then you don't need a tool to insert your I/O wiring. This can simply be inserted into one of the terminals. If we then want to extract a wire, we will need to use a smaller screwdriver such as the one shown. We can see that once we insert the screwdriver next to our wire, we are able to remove the wire very easily. If we look at this up close, we can see that it has a slightly longer barrel than what is found on some other wires. This wire has a 10mm long barrel. This is not necessary, however the longer barrel makes it easier to insert and remove wires from OCS I/O. Next, we will look at how to configure OCS I/O in Cscape. First, we will look at our bench setup. Here we have an OCS I/O rack, which we physically assembled in the same way as we showed before. This is connected electrically to our OCS through this CAN cable, which is a modified patch cable. We also have a terminating resistor installed on the second RJ port on the OCS I/O base, which we can see has not been powered up yet. Once we plug this in, we can see that we have flashing lights as it powers up. We can note that our OCS does not have any OCS I/O configuration done yet. Next, we will select the System menu shortcut we created on our OCS screen. When we select Enter, we can see that none of our OCS I/O bases have been configured. We will do this now in Cscape. First, we will select Hardware Configuration, and then select our CAN tab, where our OCS I/O is physically installed. This is now blank, as we have not done any configuration yet. We will then select the Add button. Then we go to the OCS I/O tab and select the CNX base shown. Instead of selecting OK here, we will select Auto Populate. This is because we are currently online with our OCS, and our OCS I/O is powered up and physically connected to the OCS. When we select this, we will then choose to auto-populate the I/O basis. By selecting this, anything that was in here will be overwritten. Once we do this, we are then given the UUID shown. This UUID is a unique number that comes with every OCS I/O CNX base. We are then asked if we want to assign this net ID to its respective bases. We will select Yes here. Once this auto-populate has located all of our modules, we will get a banner that says that the auto-populate is complete. We can then see that we have got a success with this UUID. Once we exit the screen, it will appear in our CAN IO tab. The diagram here shows our OCS IO base with 3 modules. When we look at our bench setup again, we can see that this matches the 3 modules in our IO base. We can also note that we still have flashing lights on all of our modules. Next, we will return to Cscape and double-click our CNX base to do some further manual configuration. First, we will rename our base to OCS IO_1. We will keep the network ID as 1. We have previously created a status register variable, which we will assign here. This is 15 consecutive words, and we have referenced the first element of the array. Next, we will need to assign the digital input, digital output, analog input, and analog output real-world I/O registers, where we want the OCS I/O in this base to start. In this demonstration, we want to adjust these to %I65, %Q65, %AI65, and %AQ65 respectively. As we are using variable advanced ladder, we need to reference one of the variables built into the project instead of simply entering %I65, for example. We will take advantage of some real-world I/O arrays for this and enter I followed by an index of 64. We are entering 64 instead of 65 here, as arrays are always 0-based, so index 64 references %I65. We will fill in the digital output, analog input, and analog output starts in the same way, so these will be Q64, A64, and AQ64. Next, we need to configure any I/O that isn't digital I/O. To do this, we will double-click our I/O base again and select the Onboard I/O tab. For our universal analog in, we will set the data type to 4 to 20 mA input and the data range of 0 to 32,000. We will also assign a filter constant of 3. We will skip over alarm configuration here and move on to our digital and analog inputs. Here we will enable channel 1 and make it a digital input of 24 volts. We will also enable channel 2 and make it an analog input with a data type of 0 to 10 volts and a data range of 0 to 32,000. We will also enable the analog output with a data type of 4 to 20 mA and a range of 0 to 32,000. We will also change the halt state, which is when the analog output is off, to the minimum value. Now we have 2 digital I/O modules on our base. Usually, we don't need to do much configuration with digital I/O modules, unless we want negative logic inputs. The default settings here configure to positive logic. We will keep these settings to the default for this demonstration. Next, we will double-click our ADU100 module and look at the configuration settings. First, we will set the data type for all 4 channels as J-type thermocouple. Next, we will change the periodic time of our input update method to every 100 milliseconds. This is the frequency at which this module is going to be distributing new readings for these 4 channels. Finally, we will set our filtering ability to 3 to achieve some additional stability. With our configuration done, we now need to download it to our OCS. To do this, we will exit our configuration settings and go to the Download to Controller setting. When we do this, we may get a warning that we are using Ethernet to download the configuration. When downloading, we also need to be careful that we don't accidentally overwrite our IP address to the wrong value and lose communication halfway through. Now let's return to our bench setup. We can now see that the LED indicators on our OCS modules are no longer flashing, which indicates that everything is running properly. Now let's look at the System menu on our OCS. If we use the shortcut we have created and go to the I/O configuration screen, we can see that our I/O base has been found. If we select Enter again, it will show us the populated modules along with the UUID for the base that was populated. That concludes our webinar for today. Thank you so much for listening, and the Q&A session will begin shortly.
Okay, nice and straightforward run through of the OCS IO modules. I'm not seeing anything in on it on that so far. Next week we do have a webinar on implementing a custom user interface. So the registration link is available as always for that if you'd like to see that one. Okay, as we're not seeing any questions on this, I think we can leave it there. Thank you all for joining us, and we'll see you again next week.